and welcome back. And today we're right back on the floppies, which is interesting because I wasn't actually intending that to be the case for this video. Normally whenever I make a video, I start filming on Monday. It takes me to about, Wednesday to finish filming everything. Then I start the edit, and I try to get the edit finished by Friday so I can upload it, take the weekend off. And that was pretty much exactly how the previous video on the floppies went. Got it uploaded on Friday, went to sleep feeling great, woke up Saturday morning and I said, you know what? In the previous episode, we really only tested the AC motors. It's not going to take much effort to see if the control boards are working. So I'm just going to go in and maybe probe a few things. And next thing I knew it was like 8 p.m. at night and I was still in this room probing and looking and learning about the floppies. And the more I learned, the more interesting it became. The more I realized I really need the camera out for this and show you guys. So that's where we are. I have the floppies currently on the desk sitting in the exact same state they were where we left off in the previous episode, but I have since learned a lot of really interesting information. So let's hop over to the bench. We'll take a look at where we are, what is working and what isn't, and then we'll start trying to see if we can get one of these floppies fully working so we can get it plugged into the Centurion and start testing out the FFC card. So let's hop over there and get started. All right, here's where we left off in the previous episode. We've got both drives mounted to the panel. We've got our Meanwhile supplies up here. They're on a nice little switch. If I flip the switch, both of the AC motors start spinning. The belts are totally fine. I saw that a lot of people actually asked about replacing the belts. These are not standard rubber belts. They almost feel like a fabric, and they were totally fine. So I'm just gonna leave them be until one of them gives up the ghost. If I take a disc and I slot it in, close the door, well, the clamp comes down and I can see the media is spinning correctly. But without anything plugged into our 50-pin command cables here, the drives are completely inert. So, well, let's do the obvious. Let's plug the FFC card and the diag card into the Centurion, plug the 50-pin cable from here into the FFC card, and see what happens. All right, first things first, let's get the FFC card plugged in here. But because the FFC card is 2 cards wide and the connector's on the right side here, when I slot it in, there has to be an open space between it and the next card. So instead of going to slot 7, we'll go into slot 8 here. And that should leave just enough space for, both cards to slide in. Now we need to connect up the DMA cable, and the DMA cable comes from the CPU 6 card. It plugs into the disk 2 card, and it has a third plug right here that we can plug straight into the FFC card. So with the way that the DMA cable is set up, you can have a Hawk drive and the FFC, or you could have the Hawk controllers and the CMD controller for the Phoenix drive or something like that. Now we need a 50-pin cable, which I happen to have right here. And we'll just go ahead and plug that one in on the long one down there. Yep, there we go. All right, that's going to go to our floppy drive. But before we can test out the FFC card, we need the diag card, which is this one right here that Ken hooked us up with. It has proven completely indispensable, and I use it all the time. It's fantastic. So we'll just go ahead and slot it into the last slot down here, slot 16. And this right now, I think is ready to start testing. All right, let's go ahead and get the 50-pin cable plugged into our floppy here. Now I've got 2 drives on here, but I'm pretty much only going to concern myself with getting 1 drive going. So we'll call this one that's closest to the power supplies drive A, and this one drive B. And we're just going to focus on drive A for today. And so in order to plug the floppy cable in, we need to figure out where pin 1 is. And well, they've been kind enough to mark it with a marker down here. The top half broke off here, but they're both marked red down there, and I actually pulled these PCBs off when I was cleaning it and took some nice high-resolution photos of it and actually traced it out to confirm that pin 1 is indeed on the bottom. And the FFC card also has pin 1 as being down. Now when I plug the cable in, I put the blue stripe up, so this is going to be pin 50, so we'll just plug this in right like that, and well, let's give it a test. All right, we'll flip the Centurion power on, we'll flip the data terminal power on, we'll flip the switch for the floppies, and I think we're ready to give it a test. We'll start with 07 floppy command buffer test. No, all right, that's not good. 11 error, 12 error, command buffer error. That doesn't bode well. All right, let's go with 08 floppy seek test. 08 41 error. All right, we'll do 09 as a floppy read test. And yeah, that looks just like the Finch when we were failing with it. So we'll control C out of it. Now I am curious, if I do 0F for the Finch seek test here, I get the same 41 error. And we get this error when the Finch is not connected. If I connect the Finch up, now we actually pass the seek test correctly. And just to double check, if I do the Finch aux memory test here, that actually passes. So, well, if I'm honest, it's not that surprising. It couldn't have been that easy. It couldn't have been just plug it in and go. We're gonna have to do some more in-depth troubleshooting. All right, I think it's time that we look at the manual, and BitSavers to the rescue. They just have the most amazing collection of PDFs available for download, and sure enough, they have a section dedicated to CDC, which had both the Finch as well as multiple floppy drive manuals in it. But we'll start by taking a look at the Finch, and that's what this is. This is the Finch manual, or at least the pertinent pages that I decided to print out. But what we're most concerned about today is going to be the pinout of the 50-pin command cable. Half of the pins are grounded, those are the odd number pins, and then the even pins are our inputs or our outputs. Some notable ones is that we have, head select up here for the multiple heads that are in the Finch drive. We have an RTZ, we have drive ready, we have 4 drive select here, which tells us that we can daisy chain up to 4 drives on this one command cable. I expect a lot of this stuff to be the same as the floppy. So let's look at the floppy manual. And sure enough, this is the floppy manual. Now there's a bunch of different floppies made by CDC. And on this page right here, they show the pin configuration and assembly usage of J1. Now J1 is A, and that's our 50-pin connector. So at the top of this pin configuration and assembly table, there's a bunch of part numbers. Now the most important part number on here is 75890500. That actually matches the part number that's on the PCB for drive B. Drive A has a totally different part number that's not anywhere in this list, but the PCBs have an almost identical layout. So I think we can use this 50-pin layout for both drives. Now there's some interesting things to notice in here. We do have 4 unit selects. That's just like the 4 drive selects from the Finch drive, but we also have 4 separate ready pins. Most drives, Shugart as well as the Finch, only have 1 single ready pin. So right off the bat, that's a pretty noticeable difference. Also, for example, index here is on pin 8. If we go back over to the Finch here, index is on pin 20. So we have some cabling issues, which would explain why when I plugged in the 50-pin cable, the FFC just thought that the drive didn't exist because none of the pins were going to the right places. So I made a little chart here that shows what the 50-pin looks like for the floppy on the left here, for the Finch in the center here, and we can see that everything is in a completely different place. But we're in an interesting spot because right now we don't know if the FFC works and we don't know if the floppy drive works. So even if we rewire the ribbon cable to match this new layout over here, the FFC could be bad or the drive could be bad, and we don't have any way of knowing which one is bad. So we need to find a way to test the floppy drive and get it working at 100% before we plug it into the actual FFC card. And this is the little test board that I've made up to actually test this out. It's just got some push buttons, some toggle switches, and then some LEDs for outputs. Although I think some of the outputs we're going to need to look at with the scope, because an LED is not going to show us what we're actually seeing. Now it's important to note that almost every input into the drive goes through a termination resistor. This is a 220 ohm, 330 ohm resistor that goes between 5 volts and ground. The 220 ohm resistor pulls it up to 3.3 volts, and then we assert to it by shorting it to ground. So we pull that input line low. So that's what all of these switches and push buttons do. They just pull that line low. Now for the outputs, they're expecting a termination resistor on the FFC card. But because we don't have the FFC card plugged in, we don't have any termination for the outputs coming out. So in order to be able to properly read them, I set up combinations of 220, 330 ohm resistors here as termination resistors. So I'm gonna slip this right up here and use the wiring of the drive to kind of hold it in place. And then I'm going to use a bunch of these little jumper wires here that have a female on one end and a male on the other to essentially jumper from the 50-pin cable here to our breadboard. All right, we've got everything hooked up. I've got the scope plugged into the index pin here. Our LEDs are here ready to light up. Well, let's just turn the power on and see at least if some of the LEDs are lighting up. Yeah, there we go. The yellow LED here is actually track 0. And it says a logic 1 level indicates the head is positioned over track 0. It's off, and the head is pulled all the way back with the track 0 switch pushed. So that's good. If I flip the power off here and I rotate the head out into the middle of its travel, the track 0 switch is now off. So when I turn the power on, that little yellow LED should come on. Yeah, check that out. So now we're not over track 0. That is good. But for now, let's put a disc in and see if we can see that index pulse. So we'll put the disc in, we'll close the door there. And yeah, I can see on the scope we've got our sector showing up. I will adjust it here to, yeah, about 500 millivolts per division there. So we're getting our sector pulse perfectly. And if I zoom way out here, we can see that, yeah, we're getting the sector pulse very consistently. That's working perfectly. All right, so next let's try to load the heads. That's gonna be this little toggle switch here. Yeah, I heard them load. That's awesome. All right, so the head is now loaded. Next, let's see if we can step the head in and out using our push buttons here. No. All right. No matter how I push the push buttons, the head isn't stepping. That's not great. All right, so after checking the schematic, the head stepper control is this plug right down here. And these big transistors here are actually the stepper control transistors for it. So the head isn't stepping, so the stepper motor isn't moving back and forth. But is that a failure of the PCB or is that a failure of the stepper motor? Stepper motors don't usually go bad, but we can find out if we just probe these pins right here while pushing the two buttons over here. So we'll go ahead and flip the power switch on here. And okay, so there's our two level lines there. If I push the buttons, oh, yeah, I mean, I can see those are changing. All right, so let's zoom way out here. Let's go up to like, say 100 milliseconds per division here, and we'll do a capture. All right, that's interesting. We can see that, yeah, there are changes going on, and you know what? It looks like they're timed correctly. And Well, I think I'm going to need to take a couple more captures of this and try to line them up and see what that looks like, because that's going to give us the best indication if the PCB is sending the correct stepper signals to the motor. All right, look at that. I took multiple shots here because my scope is only a 2-channel scope and there's actually 3 windings in the stepper motor. So it's a 4-pin motor. If we look at the schematic here, you can see that we've got our 3 driver transistors here, Q3, Q4, Q5. And this goes to J402, J403, and J401. So that's the first 3 pins over there that we were initially probing on. Now, I don't really know a whole lot about stepper motors, but what I do know is that stepper motors need a kind of cascading signal like this to stepper in the correct direction. And well, I tried lining it up. This is pin 1 and pin 2, and then again pin 2 and pin 3. So I took these 2 screenshots, lined them up, and redrew the waveforms down here. But well, we can clearly see that cascading across the 3 different windings in there, which means that the PCB is sending the correct signals to the stepper motor, and the stepper motor is not moving. Now, the stepper motor is not seized up because I can just grab it right here and rotate it, and there's really not that much resistance in it. I mean, it's about the same as the stepper motor in this one. So I don't know what's wrong with this stepper motor. So we're in an interesting position. We can test drive B now and see if it's working. And if it's not, it might have different faults of its own. And well, we might end up having to make a Franken drive here where we take pieces from both and combine them. But what I'm going to do now is I'm going to move my entire test harness here over to drive B and give it a test. And if it's working and stepping, then we'll just put drive A on the back burner for now. All right, the test board is all hooked up. The only thing left to do is I got to take this termination resistor pack right here off of this drive and transfer it over to this drive. Otherwise, none of our outputs are going to work correctly. All right, that's all plugged in. Let's flip the switch and see what happens. All right, our sector line here is not on. We're not getting anything out of the sector here. The door is closed. There is a disk in there, so we're not getting anything showing up on the scope for sector. That's probably not great. Let's see if we can load the heads. Yeah, okay, so head load isn't even working. Boy, all right. So this drive B's PCB seems to be very, very hurt, but I'm willing to bet that this stepper is good. So it may be time for a bit of a Franken drive. I think we need to pull this stepper out and at least just plug it into this drive to see if it works. All right, it's been a battle. As you can see, given the state of my bench here, things have not gone well. Drive B is completely missing in action. Most of it's down there, but the control board for it is right here. The stepper motor for drive B is actually here in drive A. And I've got a scope here, and I've got my 200 CD wide range oscillator here. And every time I thought I had it licked, I turned the camera on, I filmed some stuff, and then it wouldn't work. And I learned something new, so I went back and re-recorded. I have like 4 hours of footage that I just can't use. So I'm gonna rewind a bit and bring you guys completely up to speed. Now, I think when we left off, I was thinking that this stepper motor was bad. This is the stepper motor that was originally in here. And so I pulled the stepper motor out of drive B, plugged it into drive A here while I was just holding it, and it actually stepped. So I said, okay, so I pulled this stepper motor out, and I decided to double check it while it was out, plugged it in, and it stepped. And that was weird. Now, the way that this stepper motor is designed is it's a 4-wire motor. So there is a common 24 volts coming in, and then it splits out in a star pattern through 3 coils. And then each one of those coils comes back over to the control board and it runs into the 3 driver transistors on the bottom. Those driver transistors essentially just go to ground. So whenever you send a signal into the transistor, it creates a ground path for that specific coil. So if you send the correct cascading signals into those driving transistors, it's going to provide the proper ground paths for the stepper motor in the correct order, which will cause it to spin. So I thought, you know, maybe the driver transistors are bad. So I took out my multimeter and I did a diode check between the base and the emitter, I guess. I'm a vacuum tube guy and I don't know all the terminology for transistors. So it would be the equivalent of the grid and the cathode. So I did the diode check across there and 2 of them measured out to 0.5 volts. 1 of them measured out to 0.7 volts. I said, okay, so maybe we've got a marginal or a bad transistor. So I salvaged the transistors off of drive B here. I took these out, put them in. No change, absolutely no change whatsoever. So I did what I should have done in the beginning and start checking the voltages going into it. And it turns out that the stepper motor was only receiving 5 volts. Now, if we look again at the schematic here, we can see that there is a power reduction option. It uses a monostable multi-vibrator. I don't really know what this X/Y gate is. And then it has a big PNP transistor. And so what this does is that after a move or a seek operation, it's using 24 volts to seek the head. And then once the head has gotten to where it needs to be, it waits a certain amount of time, some certain number of microseconds, and then it switches that PNP on, which changes the voltage being supplied to the stepper motor from 24 volts to 5 volts, because 5 volts is enough to hold it in place, but not enough to drive it, and it brings the power usage of the motor down considerably. Well, there was a problem in this circuit, and ultimately I figured out what it was. It's the this chip right here, which is a 9602. This is the monostable multi-vibrator chip, and well, the plastic is broken on it. But at the time, I didn't notice this, and it turns out that this being an option, they had a jumper that allowed you to bypass it. So initially, all I did is I changed that jumper up so that it just gets 24 volts all the time to our center tap of the stepper motor. And that got the stepper motor moving with some proper power. So I'm gonna pat myself on the back just a little bit because I had this stepper motor so unbelievably clean and smooth mechanically that even at 5 volts, it could still kind of move the head backwards or forwards. That's 1/5 the voltage it was supposed to have, and I was still getting some movement out of it. So I have this thing buttery smooth and clean, but I'm gonna remove those pats off of my back because I just totally blanked on the 24 volt problem. So now it moves with some proper power, but we have an even bigger issue. And I can demonstrate it for you right quick. I've got my 200 CD wide range oscillator set up here. It's putting out a sine wave that's going into a little 2N2222 transistor. That's going to be pulling that step signal down so that that's our square wave going in. That's going to essentially step the head out. So we'll turn the drive on here, and I'll just push the button here to send the head out, and I'll turn it off. That is an absolute nightmare. We'll return it to track 0 by hand here. All right, there we go. We're back on track 0. You can see it is a jittery nightmare and it doesn't return like it's supposed to. There is something very wrong here. So if we look at the schematic here, the 3 pulses that are being sent to our motor are being generated by U25, which is a pair of D flip-flops, but I don't think those are the problem. So if we take a look all the way at the far left here, we can see that our step signal comes in through the step line on the far left, goes into U22. This is an AND gate that gates it with the unit select. From there, it goes out into U27. This is another AND gate that gates it with track 0 and the direction. And then it comes out of U27, goes to U28, which is an exclusive OR gate. And then it comes out of there, goes into pin 12 of U16, which is the input of the monostable multivibrator. Now it generates a 3 microsecond pulse that is used as the clock for our D flip-flops. Now I think that the problem is either in U16, U28, U27, or U22. And the reason that I think it's in those one of those 4 spots is because I was using the scope here to probe out and find out where our jitter was coming from, and I discovered something very interesting. So I have my scope probe here. I'm going to put it on pin 12. That's the input of the monostable multivibrator. I'll flip the switch on, and then I'll push the button here to send the head out. And it's working perfectly. What is going on? And then as soon as I remove the scope probe, it just falls apart. And then I gotta shut it off. What is going on? It's driving me bananas. I've been fighting this for like 3 days. So I have some theories about what's going on here. The first thing that I did was that I replaced U16. So I desoldered the IC, I pulled it out, I put a socket in it, and I salvaged another 9602 off of drive B, put it in, same behavior. Then I went one step further back, got to U28, which is the exclusive OR. I desoldered it, put a socket in, put a brand new 74 LS86 in it, exact same situation. Then I went one step further back. I pulled out U27, which is the AND gate, that's a 74 LS08, put a socket in it, put a brand new LS08 in it, and it's actually worse. That's the state that we're in right now. Now it jitters out and never returns. It's just a nightmare. Before it would kind of go out and come back, but it was very jittery. So somehow putting a new LS08 without making any other changes made stuff worse. But if I put the scope probe anywhere on that line, it cleans up immediately. And we're pretty sure it's the capacitance of the scope probe that's doing it, because I have right here a little 4.7 nanofarad capacitor. So again, if I put this between pin 12 and ground, flip the power on here, and I push the button, so if I put a little bit of extra capacitance anywhere on that line, it smooths out perfectly. Now I did get a little bit of jitter there at the end because I was just holding the capacitor in place and it was starting to slip in my fingers. But any capacitance makes it work beautifully. And I can put that capacitance anywhere on that train and it smooths out. Except for U22. If I put it on pin 10 coming out of U22, it does smooth out, but not as much if I put it after U27. So anywhere between U27, U28, and U16 smooths out, becomes nice and beautiful, exactly like it should be. So there's something strange going on here. I think we have one of 3 problems. One, the 9602 is marginal because it was a salvaged piece coming from here. I've got new ones on the way, but they're not here yet, so I'll give that a test. It could also be U22. I haven't replaced that IC yet. The third thing that I think is probably more likely is that the trace that goes from our input here on the card edge connector all the way ultimately over to our monostable multivibrator. It's very long and meandering and goes through several chips, and it crosses very close to a lot of other lines. And so there's no solder mask on this board, front or back. So it is possible that given how filthy it was, there's something underneath the chip or maybe on the back that I just haven't seen that's creating some kind of high resistance connection between that line and an adjacent line. And that is causing some noise to get onto the circuit that we end up eliminating with the capacitance of our probe or an extra capacitor that we just put in place. Now, the easy solution here is to just bodge in a capacitor and call it a day, but that's not the right solution. I want to figure out why it's doing this, where that noise is coming from. So I've got a lot more work to do on this, trying to track that down, but I'm also going to throw the ball out into YouTube land, and maybe you guys have an idea for something that I've missed. A link to the entire manual is down in the description below, so if you want to take a look through the manual and maybe throw your eyes down there, that would be mega. That would be absolutely brilliant, because I'm kind of beating my head against the wall on this. But as soon as we overcome that jittery problem, I think we are almost there. The 9602 that I replaced for the power reduction option, that one is shared with the read circuit, so it should now be working correctly as well. So we should have read, we should have seek, if we get the jittery problem fixed, seek working, we've got head load working, we've got the sector pulses. This is like 90% of the way there. We just got to get it that last 10% over the finish line and hopefully fix our jittery problem. But we didn't quite get as far as I wanted to in this episode, but we got really close to getting this drive finished. I think in the next episode, we're going to solve that jittery problem, and then we will make a custom cable that aligns all of the different pinouts of the card edge connector here with the FFC. We'll plug this back into the FFC and then start troubleshooting it. I'm skeptical that the FFC is working correctly because we had that command buffer error. That might be a DMA problem with the card itself, but that's something that we're going to have to tackle in the next, or maybe even the next episode, because if the next episode goes like this one went, it's going to take forever. But I want to thank you guys so much for watching, and I hope to see you in the next episode.